Okay, picking up where we left off. The next thing is the number of protons and neutrons of an individual atom. It's called the mass number. It's always a whole number. Mass number is not included on the periodic table because a given element could have multiple atoms and they have different numbers of neutrons. Atoms of the same element with different numbers of neutrons are called isotopes. Some examples. So we have carbon. Carbon has multiple isotopes. Carbon 12, carbon 13, carbon 14. So let's look at its mass number, its number of protons, and its number of neutrons. When it's written like this, the mass number is the number at the end. So the mass number of carbon 12 is 12. The mass number of carbon 13 is 13. The mass number of carbon 14 is 14. Now we look at the number of protons. Look at your periodic table again. Look for carbon. Look back in your notes a little bit. Carbon has an atomic number of 6, which means that carbon always has 6 protons. So carbon 12 has 6 protons. Carbon 13 has 6 protons. Carbon 14, 6 protons. These are all atoms of the same element, and we know that because they all have 6 protons. That's what makes them all carbon. The number of neutrons are different, and that's what makes them isotopes. So let's take a look here. If you want to know how many neutrons are here, you take the mass number, subtract the number of protons, 12 minus 6, carbon 12 has 6 neutrons. Carbon 13 has a mass number of 13. It has 6 protons. 13 minus 6 tells us that it has 7 neutrons. Carbon 14, 14 minus 6, it has 8 neutrons. Another possibility is hydrogen. Hydrogen has multiple isotopes. We're going to make the same type of table here. I'm going to write it differently this time. So I have capital H for hydrogen. 1, 1. Here I have hydrogen 2, 1. Hydrogen 3, 1. The mass number is going to be the top number. This hydrogen 1, 1, has a mass of 1. Hydrogen 2, 1, mass number of 2. Hydrogen 3, 1, mass number of 3. Look at your periodic table. What's the atomic number of hydrogen? What does that tell us about the number of protons? 1 proton. And if you look at the lower number in each of these, there's a 1. That's telling you the atomic number. Hydrogen 1, 1 has 1 proton. Hydrogen 2 has 1 proton. Hydrogen 3 has 1 proton. This is what makes it hydrogen. Hydrogen with a mass number of 1 will have 0 neutrons because mass number minus protons, 1 minus 1, is 0. Hydrogen 2, 2 minus 1, has 1 neutron. And hydrogen 3, 3 minus 1, has 2 neutrons. Hydrogen is interesting because most of all the hydrogen is hydrogen 1. Hydrogen 2 we see every once in a while. Hydrogen 2 is a component of what we would call heavy water. Heavy water is used for making nuclear fuels and nuclear energy. And then we have this other one, hydrogen 3, which is called tritium. And what's cool about tritium is that it glows in the dark. It glows all the time. I have a compass, and on the back it says radioactive. It has hydrogen 3 in it. It says do not open, radioactive. It glows all the time. It's going to continue glowing for the next 20 or 30 or 40 years. Eventually it will dim out and stop. But at the current time it's radioactive and it glows green. The atomic mass number is different. It shows the number of protons and neutrons, so there's a similarity. But this one is rarely a whole number. Rarely a whole number. It tends to be a decimal. As we just learned, protons are always present in whole numbers. So if the atomic mass is a decimal, do we have fractions of neutrons? So my carbon has 6 protons, and the atomic mass is on the periodic table. Take a look at it. It's the number with the decimal point, 12.011. So does that mean that 12.01 minus 6, does that mean we have 6.011 neutrons? The answer here is no. Neutrons are always present in whole numbers. Fractions of neutrons do not exist. So then why is the atomic mass a decimal? Here's the reason. The atomic mass is an average of all of the isotopes that exist for a particular element. Think about it this way. Think about a basketball game. So I'm playing basketball. If I make 4 shots and they're each 2 points, and then I hit a 3-pointer, how many points did I score? Well, here's 8 plus 3 more is 11 points. How many baskets did I hit? 4 here and 1 over here. 11 points on 5 baskets. My average number of points per shot is 2.2. 11 points divided by 5 baskets, points per shot, 2.2. Is it possible? Can I make any basket worth 2.2 points? Have you seen a scoreboard with a decimal for the points? No. Any basket in basketball is worth 1 point, 2 points, or 3 points. They are all whole numbers. No shot is worth a fraction of a point. So carbon has an atomic mass number of 12.011. Most carbon atoms have 12 protons and neutrons. This carbon has an atomic mass number of 12, and like we've seen it before, we could call it carbon 12. Could be written as this. Other carbon atoms have a mass number of 13. So we call it carbon 13. You could use this symbol carbon 14, in these examples, I'm going to show you how they're calculated. You don't need to worry too much about the details, but overall, I just want you to get the idea that it is an average. But it's not as simple as adding up 12, 13, and 14 and dividing by 3. It's going to be different. So we're going to make a table here. Here is the isotope. Here's the mass number, so this one's 12, 13, and 14. And then the occurrence, or how often does it appear? 2 R's in occurrence. How often do we see each of these isotopes? And this is important for figuring out the actual average. So here's what we see. 99.0% of all carbon is carbon 12. 0.9% is carbon 13, and 0.1% is carbon 14. And together this adds up to 100%. These 3 isotopes represent all of the carbon. So we're going to do what's called a weighted average, and I'm going to show you how to do it. And probably the most interesting takeaway from this is that you'll be able to calculate your weighted semester grades come December. To do this, we have to remember that 99% is actually a decimal. So you found your answer as a decimal, you multiplied it by 100, that's how it's a percentage. 99% is actually 0.990. 0.9%, 0.009, and 0.001. Now here's what we're going to do with these numbers. We're going to multiply the mass number times how often do we see it. So 12 times 0.990. We're going to do 13 times 0.009 and 14 times 0.001. So this number is 11.88. This one is 0.117. This one is 0.014. And if you add these together, you get 1, 1, 0, 12.011, which is the number that we found on the periodic table. This type of average, this is probably your main takeaway, this type of average considers how often do we see it, or what is its importance. Not just what is the average of these, but how does it relate to how important it is, or how often we see it. And that's how we get 12.011. Same idea, we could look at neon 20, neon 21, and neon 22. Their mass numbers, we have it 20, 21, 22. Each of these exists in different amounts. So 90.48% of all neon is neon 20. 0.3% is this one, and 9.2% is neon 22. Percentages aren't good for calculations, so we have to change them to decimals. This one is 0.9048. All we're doing is taking this decimal point and moving it left 2 places. So if it were this one, moving this one left 1, 2, 0.003. This one, 0.092. Doing the same type of thing as we did before, the mass number times the occurrence. And writing down the numbers. So we have these 3 numbers, we're going to add them together. And so we have 10, 13, 10, 16, 18, 1, that's 10, and 20.183. Now take a look at your periodic table. It's probably something ballpark, close, 20.183. The periodic table on the wall in the classroom says 20.1797. There's going to be a little bit of variation, but they should all be close.